Greetings everyone, this is Jeff Wilkerson, Professor of Physics at Luther College, bringing you the next in our series of what to look for in the night sky. We're talking about the week of September 11, 2023 this time around. So let's jump into it. Last week we thought about the seasons, right? We were looking at stars that reminded us of spring, stars that reminded us of summer, and we see the stars of fall and winter, and thinking about rotation of the Earth and orbit of the Earth, and all these fantastic things. And so we're gonna keep going with that. We're gonna think about fall because it's been on my mind as I've been watching all, not just the stars. In the last 3 or 4 or 5 days here, where I live in Northeast Iowa in the United States, we're headed to autumn, and the trees have started to turn. And the hillside across from campus here, where I'm recording this right now, just beautiful yellow starting to fill in across that hillside, and we recognize fall's on the way. We've had extraordinarily unseasonably warm temperatures too, and those have broken, at least for the time being, and it feels like fall. It feels like fall, it smells like fall, it looks like fall out there. And then when it gets dark, and I look to the east, sorry, I was channeling Robert Plant there for a moment, but never mind that. When I look to the east as it gets dark, I see the Great Square of Pegasus rising with Andromeda on the back of the Great Square of Pegasus. And I really am thinking about fall, and I'm thinking about the history of astronomy and the history of science and all of this great stuff. So it looks kind of like this. It's tipped up like a diamond right now. In the upper left corner, the third base of the baseball diamond, if you will, the Great Square of Pegasus, as you're looking east, this is just after dark. I'm going to say 9 o'clock my time here, is when I've really been out checking this out. This left corner over here is Alpheratz, and we call it the Great Square of Pegasus, but that star is actually in Andromeda, and I know we've told this story before because this is always a marker of fall, and I'm always drawn to it when I start seeing it here, so I know we've had these kind of discussions. But Alpheratz sits at the base of a V, a cornucopia of stars that stretches out, that marks the main asterism of Andromeda. So go and see if you can find that V, that cornucopia opening up, widening up at the top, sitting on the back of this great square, this great diamond as it is now, rising into the sky. And if we move out the bottom of that V, the bottom stars along this row are brighter than the top stars. They're easier to see, but the top stars are easy enough to see. And so you've got Delta, you've got Mirach, and you've got Almach. And as you go across the top, you've got Pi and Mu and 50-something out there. And so you got these stars that move across, move out that direction in this V. Now, we really love this region of the sky because if you go from Mirach up to Mu and go that same distance up again, you've got the Andromeda Galaxy, maybe the most famous external galaxy. Now I'm thinking about Rudolph the Red-Nosed Reindeer, but that's a different problem. Maybe the most famous galaxy of all up here, and it's beautiful. You've got a dark sky. You can see it without any optical aid. Let it get higher in the sky. Don't do it at 9 o'clock my time when you're looking so hard east. Wait a couple more hours till it gets up in the sky. And this looks like a big thumbprint, a big slash, a big, beautiful phosphorescent paintbrush stroke, like almost the size of the full moon, right, on the sky. If you have a pair of binoculars, it really pops out. And you can see this wonderful Andromeda Galaxy over there. Now, we love the Andromeda Galaxy because that was the first external galaxy that Edwin Hubble measured the distance to. And so this really is what showed us. At that time, we called these spiral nebulae, not galaxies. And there was a lot of debate in the community about whether these were external galaxies, big groups of hundreds of billions of stars like the Milky Way, or whether they were smaller clouds of gas within the Milky Way being our galaxy, right? And so when this debate raged back and forth, Edwin Hubble measured the distance to the Andromeda Galaxy and figured out that it was so far away it had to be an external galaxy. It had to be a group of stars like the Milky Way, big grouping of stars like that. And so this is beautiful to think about. Now, how he did that is he measured the period of a Cepheid variable star. And a little over 10 years prior to his work, Henrietta Leavitt had done really great pioneering work, and she was measuring the periods of Cepheid variable stars, a type of variable star that we've talked about here before, and measuring their periods and brightnesses, and showed that there was a period luminosity relationship. So the time it took to go from bright to dim back to bright would be the period. Brightest to dimmest to brightest is the period, and that period is related directly to how intrinsically luminous the star, what that brightest bright point is, or that let's just say it that way, what that brightest bright point is going to tell you how intrinsic, the period's going to tell you what that is. And if you know how bright something is intrinsically, you know how bright it's shining, and you know how bright it appears to you, you just calculate how far away it is. Because things look dimmer the farther away they are, and we know that. That's mathematics we can do, is to say, depending how far away it is and how dim it looks. And that's so Hubble was using Henrietta Leavitt's pioneering work on Cepheid variable stars to determine the distance of the Andromeda Galaxy, getting it to be, way out there, millions of light years out there. And so this is great for us to think about. But while we're doing it, let's try something hard. Let's try an observational challenge right here. So we go out here to pi, and when we sweep up from pi, we get 3 pretty faint stars. Your binoculars will help. They're brighter than the stars around. So try if you can pick out this triangle of stars right there. Theta, sigma, and rho, Andromeda. Okay, so we've got theta, sigma, and rho right here, all between, say, 4.5 and 5th magnitude. So they're all naked eye visible, but rho is the faintest at 5.1 magnitude. And so that's going to be a real challenge to pick out. The 4.5 magnitude stars, if you've got a good dark night, and this is a great week to be doing this work. All of this work is great because the moon is near new the entire week, and so it's not providing any light, it's not providing any interference for this. So let's give this a try. So go up and find those stars. If nothing else, you do nothing else this week, please go look at the Andromeda Galaxy for sure. But if you do nothing else this week, see what stars of Andromeda you can find. How many times have you gone out and you've actually tried to identify theta, sigma, and rho Andromeda? Why not? It's fun, right? But if we look at rho and we go just 1 degree, 1 finger width at arm's length up to the north and the east of rho, we come to our Andromeda. Now, our Andromeda is an interesting star because it's one of these Cepheid variable stars. So it's fun for us to try to look for it as we're thinking about the story of how Hubble used Leavitt's work to measure the distance to the Andromeda Galaxy. Because he looked at a Cepheid variable star like this, and here's one very nearby. This one's in the Milky Way galaxy. It's one of our stars in our galaxy, and it varies from 7th magnitude to 14th magnitude. At its brightest, you're going to need binoculars to see it, and a telescope wouldn't be terrible. At its faintest, you're probably not going to see it. You need a pretty big telescope to see it. So it changes brightness dramatically with a period of about 400 days, which again, using Leavitt's work would allow us to understand how intrinsically bright it was, and we can compare that 7th magnitude to how intrinsically bright it was and get its distance. Now that means over the course of 200 days, 6 or 7 months, over the course of the next 6 or 7 months when this region of the sky is visible, it's going to go from brightest to dimmest, where you can't see it at all to where it's fairly bright, shows up easily in binoculars to where you can't see it at all. Now, when it's at its brightest, it is the brightest star that you'll come to as you go up this direction from rho, as you move that faint 1 degree up that direction. So, if you love long-term projects, and I know you do, we've talked about many of these before, here's a long-term observing project. Go out, get your binoculars, get rho, find sigma, theta, and rho, sketch the region, and look to the north and the east of rho in your field of view, and sketch whatever you see. And do it each week. You do it once a week or once every 2 weeks or something like that for the next 6 months. Okay, if you do it once every 2 weeks for the next 6 months, you're going outside and you're making 10, 15 measurements. And see what you see over there, and see if you see R appear or disappear from your field of view, and notice it getting brighter relative to rho. It can be a beautiful, fun project if you're looking for something to do over the course of the next several months, to watch that star blink out. Think about a history of Cepheid variable stars and the measurement of the distance to M31 when we learned that our galaxy, the Milky Way galaxy, is just one of hundreds of billions of galaxies in the universe. One last thing for you. You do all that, this is great. You've found alpha, delta, mir, rachel, mach, mu, pi, rho, sigma, theta, and Andromeda. You're learning the stars of Andromeda. You're looking for a Cepheid variable star. You find M31. If you drop down from Mirach, the opposite direction, a little bit less. So this you go up, and you find M31, go the opposite direction, and you find M33. It's a little bit closer to Mirach than M31 is, but they're almost on a straight line down here. This is across the border in the constellation of Triangulum, but it's a big, beautiful face-on spiral galaxy, and it's big and sprawling, but it's faint relative to the sky background. That is to say, its sky brightness, its brightness is low, and it tends to merge in there. I've had my best luck seeing it. Binoculars will do this for you. Telescopes tend to wash it out. You can see it, but it's hard. So binoculars, good with binoculars. But even with your naked eye, I have seen this and the good dark skies in the mountains with just my naked eye. But while I've been lying in a sleeping bag trying to sleep in the cold ground, looking up, I can see M33 shining there along with M31. So give that a try too. Drop the opposite direction. See if you can see yet another galaxy other than M31. So this is what we got for you this week. The stars of Andromeda, a wonderful Cepheid variable star as a hard project for you to think about working on. And M31 and M33, two big, bright, beautiful spiral galaxies. As always, everyone, thanks for watching, and we really hope you have a great week ahead and get some observing in.